Hi everyone, it's me, Mr. Younger. I'm just here to teach the Physics 202 class. We were supposed to meet today, but I've got a medical procedure happening and I'm not able to attend class, so I'm just recording the last couple of examples from Chapter 21, mainly on transformer equations. So I wanted to do a couple examples, and that'll basically finish all of Chapter 21 for us. So let's go ahead and get started. I'm going to record this video, of course, and then post it on my YouTube channel. But then you'll also be able to see it because I'll post a link to it uh, in our Canvas course. So let's go ahead and get started. I'm going to share my iPad screen real quick so everybody can follow what I'm writing. Now I gotta make sure I'm on the right page. I am, so that's good. All right, so the first example we're doing is about the transformer equation, and I want to remind you guys that if you look in your book, Figure 2122 has a picture of like a Dominion Power type employee, what we call a lineman. He's actually in a bucket truck, and he's up high next to what looks like a big gray barrel, or even like a too tall of a 5 gallon bucket mounted on a telephone pole. That big gray barrel slash bucket is really a transformer, and it's been engineered over years to become a really highly efficient thing. It basically takes the line voltage that comes along the edge of the road or sometimes underground, which my father, who worked for Dominion Power, told me was on the order of like 15,500 volts, and that transformer steps it down to a more reasonable figure. Actually, a transformer can step, depending on its design specifications, they can step down a really big voltage, like on the order of 2 million volts, can step it down to even 15,000 or something like that. But often the ones that you see in neighborhoods are on the order of 15,500 volts, or maybe quite a bit smaller. I think my dad mentioned there was a 12,000 version as well. The whole reason being that if you send it with higher voltage, then you can send it with lower current, and the power loss due to the heating of the wires is proportional to the square of the current times the resistance of the wire from end to end. Uh, that P equals I squared R formula tells us that if we reduce the current, let's say by a factor of two, then we actually reduce the power loss, which is just wasted energy for the power company. We can decrease it, even though we only decrease the voltage by a factor of two. We can decrease or excuse me, even though we increase the voltage by only a factor of two, we can decrease I said it wrong again, sorry. Not only can we not decrease the current by like a factor of two, when we do that based on P equals I squared R, that would actually reduce the power by a factor of four. If you reduce the current by a factor of 1,000, then you're going to actually reduce the power loss by a factor of 1,000,000, because 1,000 squared is 1,000,000. So that's the main impetus for doing this. And now I'm going to go ahead and show you what a transformer looks like in sort of the basic schematic diagram, not the technical engineered brilliant device that saves so much money and everything that they show in Figure 2122, but just a typical transformer that you could make on your own. Normally, when you see the transformer, it will be something like, I usually call it the belt buckles that you use, like when you were a kid, you might have did a Thanksgiving play or something for your elementary school, and inevitably, if you did that, what you discovered was that the you had to wear this goofy belt to match the pilgrims, and the goofy belt always had this big rectangular belt buckle on it. So that's sort of what I picture as a transformer, the core part of it, which is really the metal that allows it uh, to boost the current up or down. So I've drawn this. Actually, I don't know what just happened with that. There you go. I'm actually in the process of trying to move this a little further from the edge, but I'm not sure I'm going to be able to. Let's see what I can do. Okay. So yeah, that leaves me a little bit more room. So in general, this would just be a chunk of iron that is actually a three-dimensional object. So maybe I'll draw this so that you can see that it really is a three-dimensional object. This is looking at the top of the whole section. And then, of course, that also can be seen like this way. And then this part comes down here. And again, we're like that. That would be the three-dimensional variety of the basically the iron ring that you could use to transform current and voltage. So what's going to happen is we'll have a wire that comes in, and that wire will come in like this, and will go around the transformer, and we should actually be imagining it going into that hole, for instance. And it could be any number of turns there. We're going to call these turns N sub P for primary, and the voltage input is coming through that wire or is set up across that wire across that particular side. Now, on the other side, we would wrap it with wire as well. So this side might look like this. And the main thing is you definitely want a different number of coils of wire on the two sides because the number of coils of wire is going to be what dictates exactly how much the current is dropped or increased and how much the voltage is dropped or increased. So the outside is going to have V output, or actually I'll call it V secondary, just like in this case, that is V input, but I'm also going to call it V primary. And this one is going to be V output, but I will also call it V secondary. And this number of turns would be N secondary. Now, now that we have that picture, I will tell you, and your book shows it with a lot of little lines, because it turns out eddy currents can actually be created inside the iron ring that we're using there. And when those eddy currents appear, they're stealing some of the energy from the transformer, and therefore making it less efficient. Ideally, we shoot for close to 100% efficiency, and this isn't like a motor or something, so it's actually quite capable, or engine I should say. It's not like a heat engine, so it is quite capable of getting near 100% efficiency if properly engineered. So what we're going to start off with is, remember that Faraday's law is the induced EMF is equal to negative N times d phi sub B. Ooh, let me rewrite that. I just slipped into my calculus-based physics class rather than my algebra-based physics class, so that's not good. But anyways, it's the Faraday's law says the induced EMF, that fancy-looking E there, is equal to the number of turns times delta phi B. That's the change in the magnetic flux divided by the time required for that change. Now, if we are actually able to make this transformer super efficient, then basically the flux that you'd see in the primary coil could be very, very close to being equal to the flux that you'd see in the secondary coil. So from this, we can say V primary is equal to negative N delta phi B over delta T, and V secondary, and this should be a P there too, sorry, and V secondary would be negative NS delta phi B over delta T. So we're going on the assumption, since I didn't put any subscripts on the changing flux, the delta phi B over delta T, that is, if we model this or engineer this transformer sufficiently, then that phi B over phi T over delta T should actually be the same, or very close to the same, for both coils. That means we could say delta phi B over delta T for the primary is equal to delta phi B over phi delta T, excuse me, over the secondary. And because of that, and these two equations up here, we can end up seeing that VP over NP is equal to VS over ns. That just comes from solving those two top expressions, the VP equals negative MP delta phi B over delta T. If I solve that for phi B over phi over delta T, or if I solve that for delta phi B over phi T, why do I keep saying phi there, over delta T, then that would be VP over MP. And if I do the same thing for the secondary equation right here, you'd see that if you solved for this quantity, it would be VS over ns. That's why these two things are equal. That being said, you can use this version, and that's normally what I use just because I pretty much don't memorize it. I remember how to get it and do it that way. But that's certainly an acceptable version. When your book does this, they actually write it a slightly different way, but it's completely equivalent. So I'll give you both of them and just know that you can use them. So it's V secondary over V primary is equal to the number of turns in the secondary divided by the number of turns in the primary. So that's the equation that your book states, what they call equation 21.6. And that's the one we're going to use. Now, in addition to that, I want to tell you how this is going to matter because, like I said, P equals I squared R suggests that we should actually reduce the current going through the wire. And if we reduce the current, we'd have to do something else with the voltage. It turns out that since P is also equal to IV. And if we wanted the power in to be equal to the power out, then what you'd say is uh, P in equals P out. Again, that's the model of a perfectly efficient transformer, but we don't have a perfectly efficient, but we can assume it's very close to perfectly efficient. So we're going to say P in equals P out. That means I in, or excuse me, I primary times V primary is equal to I secondary times V secondary. So if you do that, then you could see that I secondary over I primary is going to be equal to V primary over V secondary. So what that means is if we actually step up our voltage, let's say V secondary equals 10 times V primary. If I actually did step that up, then IS over IP would equal VP over 10 VP. You can see that the VPs cancel out like that. And what you now see is that I secondary is going to be equal to 1/10 of I primary. In other words, when we step up a transformer by a factor of 10 for the voltage, then we're stepping down the current by a factor of 10 as well. So if I increase the voltage by a factor of 10, I automatically decrease the current by a factor of 10. That's what allows us to do what we're going to do, and that's also what allows us to save so much money in terms of the power company saving money by not wasting as much electricity. So with that being said, let's look at example 2110. So here's example 2110, and I'll read it for you, but you should probably refer to your book as well, uh, so you can, more thoroughly understand it and look at the work as well. It says, example 2110, a cell phone charger. The charger for a cell phone contains a transformer that reduces 120 volts AC to 5 volts AC to charge the 3.7 volt battery. It also contains diodes to change the 5 volt AC to 5 volt DC. Suppose the secondary coil contains 30 turns and the charger supplies 700 milliamps. Calculate A, the number of turns in the primary coil, and B, the current in the primary, and C, the power transformed. So I'm going to go ahead and write down what we want here. It says a charger for a cell phone contains a transformer that reduces 120 volts to 5 volts. So what that means is V primary is actually equal to 120 volts, and V secondary is actually equal to 5.0 volts. So that's what we know there. Then they say, suppose a secondary coil contains 30 turns and the charger supplies 700 milliamps. So N secondary equals 30 turns. And they also said specifically that the charger supplies 700 milliamps. So that is I secondary is equal to 700 milliamps because that's the actual output for the charger. So for part A, they're asking specifically for the number of turns in the primary coil. So they want to know NP equals question mark. Part B, they're saying the current in the primary, so they want I primary equals question mark. And then part C, they want to find the power transformed. So P equals question mark, but we'll make use of P equals IV, obviously. So solution, I'm going to use V primary over N primary is equal to V secondary over N secondary. And I can also realize it's going to be the reverse of that for the current. So I'm going to say I primary over N secondary is equal to I secondary over N primary. That way you can see that it's the reciprocal relationship so that when V goes up, the I goes down. So let's start off with part A. Oh, and I'm also going to use P equals IV, which could be written as I squared R, but in this case it's probably smarter to do this. So let's first off figure out what the number of primary turns are. What I have from the VP over MP equals VS over NS, I have 120 volts divided by NP is equal to V secondary, which is 5.0 volts, over N secondary, which is 30. So whenever you have this, two ratios, or in this case, two rates, equal to each other, it's a proportion. And the way we solve that is we cross multiply. And by the way, in arithmetic, this is really the only time you're supposed to cross multiply. I know I keep running into students when they're working on their fractions and stuff, and they tend to try to cross multiply sometimes when they're doing either addition of fractions or when they're multiplying fractions. That's not a thing. So please keep that in mind. Don't feel bad. It's okay. A lot of people made the mistake, but the main thing is just don't do it. So when I cross multiply, what I mean is I'm going to take the numerator of one side and multiply it by the denominator of the other side. So in this case, I'm going to get 5.0. I'll leave the units off because it just gets it confusing, times NP. Now I'm going to set that equal to the other cross multiplication, which would be the numerator on this side times the denominator on that side. So 120 times 30 is going to be 3 times 12 is 36, and then I get two zeros, so this is going to be 30. Well, let me write it with a marker. This is going to be 3600. So now that we can see NP can be solved by dividing both sides, or it can be solved for NP by dividing both sides by 5.0. And remember, that's 5.0 volts, and the 3600 is technically volts times number of turns, so that's volts as well. So when we divide it, we're just going to get number of turns. 3600 divided by 5. You can tell that 100 would be 20, so this would be 36 times 20. That might be a little more complicated to do in your head, but I'm going to go ahead and take 3600 divided by 5, and that's going to give you 720. So NP has got to be 720 turns. So that is the answer to part A. The big thing is when using this transformer equation, you just got to keep your wits about you and realize which one's primary, which one's secondary, and from that, once you get that, you can just plug it in the equation, either the equation that I gave you or the form that the books gives you. For part B, it wants to know the current in the primary. So now I'm going to use the IP. So this was part A. Part B, now I'm going to use the IP over NS is equal to I secondary over N primary. And plugging these numbers in, what I know is the secondary, and now I know both of the ends, so I can write I primary, which is what we're asked to solve for, divided by n secondary. The secondary was the 30. That's equal to I secondary, which we found was 700 milliamps. And notice by putting it in milliamps, that just means the current's going to come out in milliamps as well. And now the N primary we just discovered was 720 turns. So we've got that. Again, we're going to cross multiply. So when I multiply 30 times 700, we can see that's going to be 21,000, but I'm going to double check that just because it's really easy to make mistakes. 700 times 30 gives me 21,000. So I'm going to get 20, well, I'm going to write it with a pen too, 21,000. And that technically is units of milliamps times turns. And I'll just say T for turns. Actually, let me say capital T for turns. Not to be confused with Tesla, but the main thing is I just wanted to point out that it's milliamps times turns. Now I'm going to go ahead and cross multiply the other part, which is IP times 720, and set that equal to it. Well, IP times 720 is just 720, specifically 720 turns, so I can put the T in there just if you want to keep track of that, times IP. So now all I have to do to solve for IP is I divide both sides by 720 turns. And you can see that the turns is going to cancel out here just like it's going to cancel out here. And basically I get 21,000 divided by 720. And that becomes I primary is actually equal to 29.16, or actually 17 milliamps. Again, it came out milliamps because we put it in milliamps. If we put it in kiloamps, it would come out in kiloamps. If we put it in amps, it would come out in amps as well. Now, technically speaking, all these numbers seem to have had at best 2 sig figs. There's a 120 that could be 3, and then there's a 700 that could literally be 1. But I'm going to assume everything was 3 sig figs. We didn't do any adding or subtracting, so, or excuse me, it was 2 sig figs, and we didn't do any adding or subtracting, so the answer should come out in 2 sig figs. That means I'm going to underline the 1 and 7 because they are not significant digits. So that's the current that comes in. So notice by having 29 milliamps coming in, we actually stepped up the current, even though this is not called a step-up transformer. Step-up transformers mean you're increasing the voltage. Step-down transformers mean you're decreasing the voltage. Their names are based on voltage, not on current, in other words. So this one stepped up the current of 700 milliamps, or excuse me, stepped up the current from 29 milliamps to the secondary, which was 700 milliamps. And that's part B. Now let's do part C. Part C was specifically the power transformed. So I'm going to say C, power transformed, is equal to I times V, which I could call this I primary times V primary, or I could call it I secondary times V secondary. Either one doesn't really matter. I'll do both just to show you that it doesn't matter. So P trans is equal to I primary, which we said was 29.17. Notice I've got the 2 extra non-significant digits, so I'm not, twice rounding, so this comes in handy. So that was my I primary. Now I need to multiply that by my voltage primary, which was 120. And when I do that, I'll say times 120, and this is actually 3,500. But because the milli's in there, it's 3,500 milliwatts, which means P transferred or transformed is actually equal to 3.500 watts. In other words, to convert it from milliwatts, we have to divide by 1,000, and that puts a decimal right in between the 3 and the 5. So that is the answer to part C. But as I said, I told you guys you could actually do it the other way as well using I secondary and V secondary. So let me just verify that for you. So I secondary times V secondary would be, in the case of I secondary, we got 700 milliamps. And in the case of V secondary, we got 5.0 volts. So this is going to come out in milliwatts again. So 700 times 5 gives me, of course, 3,500 milliwatts. And obviously, that's the same thing as 3.5 watts. So that verifies that. This would normally be the time where I ask you guys for questions. Obviously, I'm recording this a priori and without you being here, so you can't really use. You can't really ask me any questions. Let's go ahead now and do example 2111. So I'm going to say example 21-11, and now I'm going to read it. Transmission lines. An average 120 kilowatts of electric power is sent to a small town from a power plant 10 kilometers away. The transmission lines have a total resistance of 0.40 ohms. Calculate the power loss if the power is transmitted at A, 240 volts, and at B, 24,000 volts. So this is just a direct application of the principles that I told you. We're going to use the actual transformer equation, but we're trying to use this to show you that by transmitting the power at 24,000 volts, we're going to lose a lot less power than we do at transmitting it at 240 volts. So let's begin. First off, what I need to do is figure out if they're actually sending 240 volts with 120 kilowatts, then I should be able to figure out exactly what the current will be. So let's start off with that. So P equals IV tells us, actually, let me go ahead and write down the figures that they gave us first because I read them to you, but I didn't write them down. So first off, they said an average 120 kilowatts of electric power is sent to a town. So P is equal to 120 kilowatts. Now they said on average, so that's I guess what they mean is per house maybe or something. I don't know. 120 kilowatts is not very much. That's the main thing I want to point out though. But that's the power, and then the power plant is 10 kilometers away. That doesn't matter really to anything. That's just a figure in there. Sort of, you can think of it as a quote unquote trick question. It says the transmission lines have a total resistance of 0.40 ohms. So R is 0.40 ohms, like that. And what we want to know is P for 240 volts is question mark, and then we want P as 24,000 volts is equal to question mark. So, excuse me, yeah, the power loss. So this is something different than the 120. The 120 is sort of just a measure of how much is going out. So now I'm going to go ahead and say P is equal to IV, and that means that, for instance, we can solve for the current by taking the power and dividing it by the voltage. So, and this is one of those calculations that I told you every, grown up should learn, because you should be able to look when you buy a power tool or something like that, a space heater or whatever, you should be able to look at the wattage of that device and figure out how big of an extension cord you would need based on the current. Well, you can't figure out the current unless you know how to do this math. So once you figure out what the current will be by taking the power and dividing it by the voltage, then you can look up what gauge wire, or specifically just look for a wire at a hardware store, extension cord that advertises that it can handle that much current. So let me show you how to do this. It's pretty straightforward. We're doing 120 kilowatts divided by, of course, the voltage, which we said was 240 volts. I'm going to pretend like these are both two sig fig numbers, so I would put a underscore under the 20 like that, under the 120 like that, so that we see that this is going to be two sig figs. If I take 120 and divide it by uh, and this is going to come out in kiloamps, which we're going to have to change, of course. But if I take 120 and divide it by 24, I get 5. So this is 5.00. And remember, this comes out in kiloamps, which is in fact 5.00 times 10 to the third amps. So that's how much power or how much current actually goes out in this scenario. So now, if we want to calculate the power loss, we'll say P equals I squared R is the power loss. So when I use the low voltage, I'll call that P sub L for P low, and I'll just say PL. Uh, I'll say that's low V. Actually, let me write it a little clearer. Instead of just calling it low with a V after it, that looks like LOWV. I'm going to say low V. And that's what I'll indicate it by, is just the L. In this case, it's going to be, in fact, the 500 amps. Whoa. Oh, excuse me. It's supposed to be 5,000 amps. And, uh, oh, stupid me. I did 240 volts instead of the 120 volts. That was if the okay. Reading back on the question, there's an issue where it says an average 120 kilowatts of electric power, a small town. Oh, gotcha. Sorry about that. It was not sent out at 120. The power is 120 kilowatts, but the voltage sent out is actually 240, not 200, not 24. I don't even know why I wrote 24, where I even got that. Sorry about that. So this actually turns out to be a boo-boo on my behalf, just, and I don't even know why I made the boo-boo. But anyways, here it is. Let's fix this too. It comes out at 240. That's just the way we send out electricity in some sense. Specifically, what we have is, and I mentioned this in class already, we have triphasic 120 root mean square voltage. And each of those are lagged by 60 degrees. So you've got three different sine waves. One peaks at, 90 degrees because that's where sine waves peak. Then the next one peaks at 90 plus 60. And then the next one peaks at 180, or excuse me, 90 plus 60 again. In doing so, that makes the peak, which would normally be 120 times the square root of 2, which is quite a bit bigger, like on the order of 170, that being a positive peak of that around 170, but that happens to be exactly in line with one of the other ones' trough. So, because you got three sine waves staggered, one of the troughs of one of those sine waves is exactly lined up with the peak of one of the sine waves. Therefore, you get a difference of 170 up and 170 down. That gives you the 240. So that's why it's actually 240, and I should have been more careful about that. I don't even know why I wrote 24 instead of 240. That was the screw up. So this turns out to be 0.500 kiloamps, and that makes this, instead of 5 times 10 to the third, it makes it 5 times 10 to the 2. So now that we have that, we can realize that that's going to be essentially 500 amps. So when I do the power loss due to the low voltage, that's I squared R, then the current going out is the 500 amps, and that's got to be squared times 0.40 ohms, and 500 squared times, still not doing it, times zero point 0.4. Been easier just to do the math in my head. That gives me 100,000 times 10 to the fifth watts. So it's basically 100,000 watts. Now, if we look at P high voltage, which we're just going to call pH, that's also equal to I squared R. But in this case, if we actually step the transformer up from 240 to 24,000, we can see that that's a factor of 100 higher. So if the voltage went up by a factor of 100, the current should go down by a factor of 100 based on the transformer equation. Let me show you that real quick. I primary over N secondary is equal to I secondary over N primary. Again, that's just the way I derived it. So the primary was supposed to be 500 amps, and the NS, what I might just call that N. Uh, no, actually, since it's stepping up the voltage, I know the secondary is going to have a larger number of turns. So I'm going to say it's 100 times N primary. Because again, we know that the voltage is stepped up by 100, so we need the primary coil to be smaller by a factor of 100 than the secondary coil. So now the I secondary is what we're solving for, and that I secondary is that divided by MP. And if we do that cross multiplication, what you can see is that I secondary turns out to be 500 amps divided by 100. So in this case, we get 500 divided by 100. That's going to give me 5 amps. And that quantity is going to be squared, and it's still times 0.40 ohms. So in this case, we're going to get 5 squared times zero point 0.4, which gives me 10.0 watts. So you can see basically it's a factor of 10,000 more power when we use the low voltage than when we use the high voltage. So hopefully that problem, despite my little careless mistake of starting with the 24 instead of 240, I don't even know why I wrote it. But anyways, that should do it. The remainder of chapter 21 is basically explaining inductive charging, like how you can charge your cell phone by laying it on a charger instead of actually plugging it in. That also talks about induction stoves, all sorts of stuff. They talk about how to read and write memory in a computer, both what we used to do, which was on tape, and then we ultimately did DVDs, and then later even other complex devices, and talks about memory. It talks about a lot of applications. It's just the kind of stuff that if you're interested in any of these fields of interest, whether it be medicine, electronics, or computers or whatever, you should read those. But again, I don't necessarily take questions out of those. I just take questions out of the examples in the non-optional sections. So I hope this helped everyone. I'm going to go ahead and end this video, and feel free to give me a call or send me an email if you have any questions.